Good morning, ladies and gentlemen. I'm sorry that I'm not able to be there with you today. I'm thinking about you guys and I miss you. So let's talk a little bit about our new topic. Our new topic is momentum. You guys think about it. What do we know about momentum? Right? What does momentum sound like? Well, momentum is the quantity of motion of having a moving body measured as a product of its mass and velocity. Kind of think about inertia. Remember inertia, right? The tendency to change an object's motion. Right? Well, we think about how hard is it to stop a moving object, right? When you have momentum, right? Momentum, we have mass and we have velocity. Now, remember, when we talked about inertia, the only thing that really relied or was important with inertia was mass, speed and matter. Well, momentum, which is very similar to inertia, has mass, that's very important, but it also now relies on velocity. We have our equation right here, P equals mv. Ladies and gentlemen, this is on page 6 of your reference table, right? Everybody should be looking at that. Everybody should be trying to find that equation so you know where that is. Our units here are kilograms, because that's our mass, times our speed or velocity, which is meters per second. Or you'll also see it as newtons times seconds. Momentum is a vector quantity. So what does that mean? What that means is that it relies on magnitude and direction. You need both the magnitude and the direction. Direction matters, right? So now we're going to be dealing with, you may have a positive momentum or a negative momentum. Remember, that negative sign just means you're going in the opposite direction. Both of our relationships here with mass and momentum and velocity and momentum are direct. So what does that mean when we talk about direct? Well, if mass increases, momentum increases. If velocity increases, momentum also increases. Both are direct relationships. Now, let's do an example. So let's look at this example. We have two trains, Big Red and Little Blue, that have the same velocity. Big Red, however, has twice the mass of Little Blue. Compare the momentum. Well, what we have here, right, if we say that we have the momentum, so we're going to use a capital P there, is equal to the mass of Big Red, so we're going to say m sub r times some velocity, right, because it has a velocity. Let's compare that to the momentum of Little Blue. Well, it says Little Blue has twice the mass, so 2m sub blue times the same velocity, so we can just say v. Well, what's happening here? The momentum of Little Red, of Big Red, just has some mass, right? But the mass of Little Blue, is twice as big. So that means that Little Blue will have 2 times momentum, because they have the same velocity, but Little Blue has a larger mass. Remember, mass and momentum have a direct relationship. Let's try example 2. It says the magnitude of the momentum of the object is 64 kilograms times meters per second. If the velocity of the object is doubled, the magnitude of the momentum of the object will be what? Okay, well, let's first start off by seeing that we said that the momentum initially is 64 kilograms times meters per second. Well, we know that the relationship between velocity and momentum, right? Velocity and momentum is direct. So if velocity is doubled, then your momentum must be doubled, right? So 64 doubled will give you an answer of 128 kilograms times meters per second. Again, direct relationship. Whatever you do to one of the objects happens to the other. Let's do example 3. An Aiki D-3A bomber has a mass of 3,600 kilograms. It departs from its aircraft carrier with a velocity of 85 meters per second due east. What is the momentum? Alrighty. Well, ladies and gentlemen, what's the first thing we do? We say that our equation is P equals M times V. Well, let's plug in what we have. It says our mass is 3,600 kilograms. We are multiplying that by a velocity of 85 meters per second east. Well, our momentum just becomes, plugging that into our calculator, 306,000 kilograms times meters per second. Right? A simple plug and chug. Well, let's check out the second part. It says after it drops its payload, its new mass is 3,000 kilograms and it attains a cruising speed of 102 meters per second. What is the new momentum? What is the new momentum? And ladies and gentlemen, did you notice I forgot the direction, right? There needs to be direction. If it gives you a direction in the problem, you have to supply a direction in your answer. So our total momentum is 306,000 kilograms times meters per second east. Now back to our second problem down here. Well, let's write out that equation again. We have mass times velocity. We know that our momentum is equal to, now it's only a 3,000 kilogram mass, times its velocity is now increased to 102 meters per second. Well, plug that into your calculator. We get that P equals 306 thousand kilograms times meters per second. Well, how is that? How can that be? Well, if you notice, we dropped our mass, right? We dropped our mass, but we ended up increasing our speed, right? So what does this support? This supports that momentum of an object is always going to be conserved. Whatever your momentum is before is going to equal to your momentum after, right? Momentum is conserved. All right, ladies and gentlemen, once you have completed all the way up to example 3, make sure please to write these down in your notes. And now you are going to complete your momentum worksheet.